Hello and welcome to the overview of the NASA Measures Project Displacement Grid products. My name is Katherine Guns and I'm currently a postdoc at the Scripps Institution of Oceanography. And in this little presentation, I'm just going to give you an overview of our displacement grid products. So mainly, what are these displacement grids? How are these products created? Really sort of the methodology behind everything. And what products are available and where can you download them? So first, we're going to dive into what these displacement grids even are. So to give you an overall definition, the displacement grids are an interpolated grid product that shows cumulative displacements since the year 2010. And these are calculated from a combination of a 7-day median filtered GNSS time series solution and a long-term velocity field predicted from a geophysical fault model. So that's a pretty intense definition. We're going to break that down over the next set of slides. First, we're going to look at what these displacement grids actually look like through time, though, to give you an example. So at the far left, if we start there, what you see are two displacement grids, one for the east component of motion and one for the north component of motion. And these are at our reference epoch time zero 2010. And so this means at the year 2010, the very start of 2010, we're assuming zero displacement has occurred. But as we step forward in time, for example, at T1 equals 2017.5, we can see how much motion has accumulated over that time span since 2010. And so this motion is all due to plate boundary motion and transient motions as seen by GNSS and this long-term plate velocity model. So then as we step forward more time, we can actually see how these accumulated displacements vary spatially and temporally. So this is sort of the beauty of the displacement grid product. It's a lot easier, however, to actually see it in a video. So what you're seeing here is essentially a stack of all the displacement grids from 2010 to a point at the end of 2020. So as you watch, you can see the displacements accumulate along the west coast of California here, mainly due to San Andreas plate motion. And again, this is east and north, so you can see how they look different over time. You can also see those earthquake displacements for Ridgecrest, those were right here, and for the El Mayor-Cucapa earthquake that occurred in 2010 down here. So this is really the displacement grid product, shows this temporal evolution of our spatially continuous grid here. So now that you've seen what these look like, we can talk about how these products are actually created. So first, we're going to talk only about the horizontal motions. We'll get to verticals in a second. But for our horizontal motion displacement grids, we first start with our daily GNSS time series observations. And then we median filter those on a weekly 7-day basis to create our weekly displacements from GNSS observations as a point file. Then on the other side, we take our geophysical fault model, and this comes from the Zhang and Shen paper in 2017. And we calculated predicted weekly displacements as points and as an interpolated grid. Next, we take those median filtered weekly displacements from our GNSS, observed weekly, and we subtract the predicted weekly motions from this geophysical fault model. And this allows us to create a residual grid. So that step can sometimes get a little confusing. So the way I like to explain it is to say, in our observed GNSS time series, we see all displacements at the surface of the Earth. And what we're doing here is essentially detrending those displacements in order to see what's happening in the residual set of displacements. So we're taking everything we see at the surface of the Earth and we're subtracting that long-term velocity trend from plate motion as predicted from this fault model. And that allows us to just visualize the residual displacements left over. And so those residual displacements as an interpolated grid look like this down here at the bottom left. And that long-term plate motion, just for reference, looks like this at the top left. So then to create our total cumulative displacement grid, we add that interpolated residual grid, those short-term motions, back to the model predicted long-term grid. And this gives us, again, our total displacement in the horizontal motion. So one benefit to this whole process is that we actually end up calculating these residual grids. And so looking at these grids can actually tell us a lot about what's going on with crustal motion. These horizontal transient grids show all these short-term variable motions in the area that we're looking at. And so to give you a little bit more of a better visualization, let's look at this video here. So again, these are our weekly residual grids, which are the observed GNSS minus the long-term plate motions. And this shows us all the different kinds of cool transient activity that's happening. So we can see, for instance, post-seismic displacements from El Maricucapá and the Napa earthquake. We can see magmatic and volcanic displacements happening at Long Valley and at Lassen here. We can see creep happening at Parkfield on the San Andreas Fault. And we can see Cascadia subduction motion as well as Northern Basin and range motions. So again, this is a product that you can access in our archive, and this allows us to visualize these displacements really nicely. So next, we're going to talk about the vertical motions, which are actually calculated in a much simpler way. To start off with, we take, again, our daily GNSS time series observations, and then we estimate those weekly displacements using that median filter. And then the thing about the vertical motions is that we don't apply any kind of underlying model. We just simply take the weekly displacements, our median filter displacements, and we apply the green spline interpolation in order to get an interpolated grid, which you see here at the left as a video. So this produces our vertical displacement grid product. And so what you're seeing here for California, you can see a pretty strong signal in the Central Valley that's mainly due to subsidence caused by agriculture and groundwater pumping. But you can see some signals here in Long Valley and up at Lassen as well as stuff happening in the Salton Trough down here too. So again, this is just another product that we provide that's really useful to look at these long-term, these motions. So one critical question to ask is, are any of these uncertainties calculated? And the answer is yes. Currently, we calculate an interpolation misfit for all components, and this provides an estimate of really how much to trust the interpolated pixels that are between your data points. Right now, we are working to implement an improved uncertainty calculation that should better account for measurement uncertainty or data uncertainty, as well as that interpolation misfit. But we're putting that in the works right now. So last, most importantly, I like these products, I'd like to look at them more. Where are they and where can I download them? So right now, our current products spatially include California, Nevada, and they've recently been expanded to Oregon and Washington, as well as parts of Idaho and Vancouver Island, British Columbia, and Baja California. You can see there's some data sparsity in Idaho and Montana, but we're working on improving that. But these products are all available online on the SOPAC archive. I'm not going to go step by step through this list, but if you want to see the full list and full explanation of each one of these products, please visit the link in this QR code. And that leads you to the algorithm theoretical basis document, which is the entire measures project document that describes everything you could possibly want to know. This is our list of our horizontal grid products. This is our list of our vertical grid products, much the same as the horizontals. And we also have a list of our horizontal transient products as well. And again, check out that algorithm theoretical basis document, or ATBD. So if you're on this page watching this video and you want to go access these displacement grids right now, just scroll up to the top of this page, which is located at this link. Click here, and that should take you to this page. If you find that you're asked for a login, please use this login here provided at the top left. And if you find you're having trouble accessing the page, try entering this link instead. Sometimes the FTP, HTTP gets a little messed up. But once you make it to this page, inside the dynamic datum directory are all our horizontal displacement products. And inside the transient directory are all our horizontal transient products. So feel free to explore both those directories. Here are some references and some more web page links. And if you have any questions or suggestions or comments, please feel free to contact Yehuda Bach at this email or myself at this email here. Thank you.